When using the Abaqus software, you may have noticed that Abaqus uses a logarithmic strain to present results. The logarithmic strain is denoted by LE in the Abaqus software. In this video, I'm going to explain the logarithmic strain and compare it to the more commonly used engineering strain. To do this, I'll use a one-dimensional beam shown here. The beam is of initial length L0 and is given a displacement of delta L at one end, giving it a final length of L0 plus delta L. Before proceeding, I'd like to introduce the stress ratio lambda, defined as the ratio of the final length to the initial length. Later on, we will be using this parameter in our mathematical derivations. At this point, it is necessary to recall that the strain has no universal value and different strain measures produce different strain values. The choice as to what strain measure to use depends very much on the problem. In cases where we have small deformations, most strain measures produce almost identical results. But in cases where we have significant plasticity and deformation, like in most crash simulations, different strain measures produce very different results. Now I'll make things clear using this graph. As you can see here, for lambda values close to 1, both the logarithmic and engineering strains produce essentially the same results. But as the stress ratio gets larger, so does the difference between the two measures. The material nature plays a critical role in its response to applied loads. While most metallic and brittle materials do not exhibit significant plasticity before failure, there are certain polymers that stretch to several times their initial length before their final rupture. With this introduction, I guess it's time to get started with the derivations. The engineering strain is defined as the ratio of the changing length to the initial length, or in terms of the stress ratio, lambda minus 1. To describe the logarithmic strain, I'll walk you through an example. Let's say we have this beam of initial length L1 subjected to an overall displacement delta LT. Let's assume the overall displacement is applied in multiple increments, with each increment producing its own respective strain. Note that the initial length in each step is set equal to the final length in the previous increment. Adding up these incremental strains will yield the total strain. If the increments are made infinitely small, we'll be able to change summation to integral with the lower limit set to L0 and the upper limit set to the current length L. This integral is known to be the natural logarithm, and when the limits are inserted, we will have the logarithmic strain defined in terms of the stress ratio as is done here. Before concluding, let's review some key points. We just learned that the engineering strain is most suitable for materials that show insignificant deformation before failure, such as most metallic and brittle materials. We also learned that as long as the material response is predominantly elastic in nature, uh, most strain measures produce essentially the same results. However, when we have considerable plasticity and deformation, as is the case with most polymeric materials, we better switch to the more accurate logarithmic strain. Thank you very much.